Hello and welcome to Lecture 5. I'm Chris Mack, the professor for this class from Data to Decisions. Our lecture is the first of a three-part series of review lectures on the topic of regression. Now, I call them review lectures because I assume that all of the students, people listening to this talk, have some background in regression already. So what I'll be doing is talking about the basics of regression in a fairly detailed and rigorous way. So maybe there are, in fact, some aspects of regression that I'm going to talk about in this series of review lectures that are new to you. So don't get worried if that's the case. That's sort of my intention. But it is a review in the sense that you better already have had some background in regression as well. I'll mention that I have a review course on statistics online, and it has lectures 16 and 17 of that review course, some background on regression, which if you aren't that familiar with regression, you should go and make sure you're up to speed. So very quickly, let's start with some vocabulary that we're going to be using in this discussion. First, an experiment. I think we all know what an experiment is, but to define it explicitly, experiment is where I have certain variables, explanatory variables, predictor variables, regressor variables, all names that we can use, input variables, are going to be manipulated, controlled, adjusted over certain ranges and certain values. All the other input values are going to be held constant. Then we're going to measure a response variable. This is the output, the dependent variable. We'll call it y. We'll call the explanatory variables x, x1, x2, x3 if there's more than one, and y will be the output. Now, an experiment is as opposed to an observation, where we're not controlling the input variables. In an observation, we're measuring the various inputs and then measuring an output as well, but we're not manipulating those inputs to be at specific values. Then we'll develop a model. Model will be a mathematical function that predicts the output for a given set of variables. We'll do two things with this model. One is we'll try to match the model to the existing data that we already have, that we've already collected in our experiment. And then we'll try to match the model to new data. In other words, we want to make predictions and see how well the model matches those predictions. The first step, matching the model to existing data, is a process we call regression. This is where we're going to find the best fit values of certain parameters in that model that will adjust so that it matches best the data from our experiment. Now, I have spent a little bit of time talking about what we mean by best fit. There are, in fact, more than one definitions, more than one ways of describing a fit as being best in certain senses. There are some that are preferred over others in certain circumstances, but as we'll see throughout this course, that in fact you can define best in a number of different ways. We'll define it in one specific way here. Later in the course, we'll look at some others. The last term we're going to use a lot throughout this course is a very, very important concept. It's called the residual. The residual is very simply the difference between the experimental data point and the model. You might think of it as the error, but now you got to decide what you mean. Is it the error in the model, the error in the data, some of both? We can be a little bit more neutral in our terminology if we call it the residual. So if we knew the model coefficients exactly, we knew what all the betas were, and for any given set of inputs, the difference between our model and our data would be the true residual, which I'll give the symbol epsilon. But if I don't know these betas, I can estimate the betas with some parameters we'll call B. These are our estimates, and in fact, regression is all about trying to find these values of B. If I use my estimated parameters in the function, then the difference between the experimental data and that function will also be a residual, but we'll give it Roman letter E. not the true residual. It's the residual based on our best estimate of what the model is. Now we're going to define best based on properties of the residuals. A good model, a model that we like, that we think does a good job of fitting the data, have two basic properties. First of all, the mean value of the residuals will be small, and the variance of the residuals will be small. As it turns out, we're going to use models that include an offset and intercept. And if we do that, we will find best fit parameters, in particular that best fit offset, such that the mean of the residuals is exactly 0 every single time. So for our best fit model, we will be defining the mean of the residuals equal to 0 as just a part of our process of finding best fit parameters. Now, there'll be some small exceptions to that in some special cases we'll talk about later in the semester. But in general, mean of the residuals will be 0. For that case, it's the variance of the residuals that will be our measure of how good the model has fit the data. And we'll find out that plots of this residual versus, say, the predicted value from our model will be very useful in helping us understand the nature of how good this fit is. We're going to see graphs of these residuals being used over and over again throughout the course. Well, let's attack that question of what do we mean by a best fit. First, we'll assume that the residual, the true residual, epsilon, is a random variable. We'll assume that it does not depend at all on the input values, x. What does that mean? If it doesn't depend on any input value, whether we have one input variable or multiple input variables in our model, if it doesn't depend on the values of any of the input variables, we say that the model is perfect. The model describes reality perfectly well, and the only thing that's left over is this random component. There are no systematic components, no systematic differences between the data and the model. If we make that assumption, then we can define best, a best fit, perfectly good model to a set of data, as having two basic properties. One is that this best fit is unbiased. Unbiased means two things. One, the sum of the residuals will be equal to 0, so that there's no offset of the data compared to the model. But also, it will be unbiased in this sense. Expectation value of the estimated parameter will equal the true value of that parameter. Right? That's this equation right here. The expectation value, we use the symbol E of the square brackets. And what do we mean by the expectation value? It means simply this. I were to repeat the experiment an infinite number of times. So I let n, the number of data points, go to infinity. Then in that case, the best fit value of my parameter, my estimate b sub k, the kth value, the kth parameter, will converge to the true value. If, as the number of data points goes to infinity, the estimated value converges to the true value, we'll call that an unbiased estimate. Then we'll also want, as our best fit estimator, an efficient estimator. This is an estimator that has a minimum variance in the residuals and a minimum variance of our estimates. And we're going to talk about later on in the next lecture how we arrive at this variance of our estimate. But we want that variance to be as small as possible. We say it's efficient because if that variance is small, that means we don't need a whole lot of data points to get a good fit. If that variance is large, then we have to make up for this large variance by having more and more and more data points. And as we know, collecting more data is expensive. If one estimator can give you a good estimate with 20 data points and the other estimator requires 50 data points, well then the one that can give you a good estimate with 20 data points is more efficient. So minimum variance will be a key that we're looking for. sometimes we like the idea of maximum likelihood from a philosophical perspective or an intuitive perspective. And I'll talk about what that means in just a second. And the fourth thing that we would like from our best fit estimator is that it be robust. We'll have lectures on robust estimators later on in the semester, but basically what it means is if I have a bad data point, how much does it screw up my answer? Non-robust estimator could get completely screwed up, give you very, very poor estimates if you had one really bad data point. But a robust estimator is one that can handle a few, maybe even quite a large number of bad data points and still give you reasonable estimates. We're going to talk about robust estimators later. Not going to discuss it near term. But let's see what we mean by maximum likelihood. Now, again, in lectures 16 and 17 of my review course on statistics, I talked about maximum likelihood estimation. If this is brand new to you, you might want to go and watch those review lectures first, listening to what I'm about to say. But maximum likelihood estimation begins by defining a likelihood function. A likelihood function is just this. It is the probability that we would get this exact set of data, given that we have a model and certain model parameters. So I've got a model that accurately describes what's really going on. But this model includes a piece of it, this is a random piece. This epsilon has a probability distribution function that results in some random variation. So any given data set could happen, but is more or less likely depending on the model and the probability distribution function. So what I'm going to do is calculate the likelihood of getting a specific set of data and then ask what parameters of that model would produce the maximum likelihood. That is, what parameters of the model maximize the probability that the data set that I actually got, that I actually measured, would have come about. To do that, and we'll show you exactly how we do that in just a second, to do that, I need to have an assumption about the probability distribution function of the residuals, epsilon. And then I will take the partial derivative of this likelihood function with respect to the specific parameters, set them equal to 0. That's how we maximize. Derivative, set it equal to 0. Values of the parameters that creates that 0-second derivative. And do that for every single parameter, unknown parameter that we're trying to fit. Solve those simultaneous equations and you'll get the parameters that produce the maximum likelihood. Well, the easiest way to see how this is done is with the simplest model that we have available to us, a straight line. Remember, I said linear regression is regression where you're linear in the model parameters. So this will be linear regression. But the fact that we're using a model that's a straight line is just one example of a model. We're going to be able to do modeling for all kinds of functions. So if this were xi squared, for example, natural log of xi, that would be linear regression as well. But for the algebra, the simplicity of the algebra to show you how it works, we'll use a straight line model first. Now, notice when I specify the model, I'm specifying two things. I'm specifying the functional form of my model, how the output varies with input variables xi, for example. But also, I'm specifying the probability distribution function of the residuals, random piece of my stochastic model. This random piece we will assume here to be a normal distribution, zero mean, and a fixed standard deviation, sigma sub epsilon. In other words, we call this assumption IID, independent and identically distributed. IID. Independent meaning each value of yi is independent of all the other values of yi. Each value of the residual epsilon sub I is completely independent of all the other values of the residuals. They're not correlated at all. And they're identically distributed, this normal distribution, in a fixed or constant standard deviation or variance. Now, since each data points are independent, the probability of getting a specific set of yi's be the product of the probabilities of each individual yi. This comes from the assumption of independence. So my likelihood function will be the product of the probability of getting any specific data point. And that probability is the probability of getting any specific residual data point, since the model is fixed. Now, since these residuals are IID normal, and I know the equation for a Gaussian normal distribution, it's this exponential function, I will simply plug in the equation for the probability of a normal distribution, take the product of all these things, and that's the resulting likelihood function. You see we have n data points, so I have n normal distributions all multiplied together. When I multiply exponentials, I can combine all the exponentials and I get a sum of the things that are in that exponential, and there it is. This summation, I to n, of the residual squared divided by variance of the residuals, we're going to give a special name. We're going to call that chi-square. Chi-square is just the standard name that people give to this particular function. It's also called the weighted sum of square errors. So epsilon residual, true residual is the error squared. Here's the sum of the square errors. Now I'm weighting that sum of square errors by dividing by 1 over the variance of the residuals, the true value of the variance. So this is the chi-square. And maximize L, I want to minimize chi-square. Right? If you go look at that exponential, it's pretty obvious that you get the largest L possible by having the smallest chi-square. I will minimize chi-square, taking the derivative and setting it equal to 0. I'll do that for every single coefficient in my model, beta sub k. In this case, we're going to do a straight line model. We'll only have beta 0, the intercept, and beta 1, the slope. But if I had a more complicated model, I would do this for every single parameter in the model. Every time I do that, I'm going to get equation. And if I solve all of these equations simultaneously, I will have my answer, best fit set of coefficients. Well, we can do that very simply. The algebra is pretty simple for the case of a straight line model. Residual is the data point minus a linear model, straight line model. Plug that residual into my chi-square formula right here and take the derivative. Let's take the derivative first with respect to the intercept. So I take the derivative, I multiply by 2, take the derivative, multiply by what's there already, take the derivative of what's inside. With respect to beta 0, it's just minus 1. And then there's my equation. A little bit of simplification shows me, and solving for beta 0, I'll now change the name from beta 0 to B0. Okay. Why am I doing that? Because now I'm going from a theory that works in general to a specific value intercept for these specific data points that I have. Because it's a specific set of data, I ran the experiment again, I get a different set of data, slightly different maybe. But every time I run the experiment, I'll get different data. I'll get a different value for beta naught. So I'll call this my estimate of the true value. That's why I've changed the nomenclature here. Now I have my estimate. The estimate for the true value of beta naught is mean value of y minus the slope times my estimate of the slope times the mean value of x. Obviously, I haven't figured out what the best estimate of the slope is, but nonetheless, this is the equation. I do the same thing. Oh, before I go on to the next thing, I might mention that this equation, here's yi, here's the model, so that's nothing more than the residual. So this is saying the sum of all the residuals equals 0. Right? So the fact that we have an intercept in our model means that the best value of the intercept is that which produces the sum of all the residuals equal to 0. The mean value of the residuals is equal to 0 for the data set. And that will be how we can think about, how we can define what the best value of that residual is. Excuse me, the best value of that intercept in our model is. All right, we can substitute this estimate for beta naught into the chi-square equation and then take the derivative with respect to beta 1, that is the slope. We do that, carry it out, the algebra, and we get the following equation, which if you go back to your standard textbooks on linear regression, undergraduate, this is probably the equation for the slope that you might have seen in the past. Now you can see where it came from. It came from this maximum likelihood estimate by taking the derivative of chi-square, setting it equal to 0. Now notice that when I look at this resulting equation, it's the same as the sum of the x values times the residual values being equal to 0. We'll see that coming up again when we talk about multiple regression and the use of matrices for doing these calculations, which will be the next lecture. Let's remember the assumptions that went into our derivation of this maximum likelihood estimate. We assumed 3 basic things about our model. Fourth thing is we assumed the model was perfect. That came first. But then we assumed that each residual was independent of all the others. Now, that's the same thing as saying each collected data point, yi, is independent of all the other data points. Then we assume that each residual, and therefore each yi, is identically distributed. And that distribution, the third assumption, is a normal distribution. So each residual is normally distributed with mean 0 and standard deviation sigma epsilon. And that's the same thing as assuming each data point is normally distributed about its modeled value, its predicted value, which is the value we get from our model, with the same standard deviation. When we make these assumptions, we call this version of maximum likelihood estimator the ordinary least squares. A lot of what we're going to do in the course is to figure out what to do when some of these assumptions are not true. And we need to rethink our meaning for a best estimate. If any of these assumptions are invalid, the consequence will be that the least squares estimates aren't equal to the maximum likelihood estimates. So I want to try to separate out this 2 set of terminologies. Least squares or ordinary least squares means one thing. Maximum likelihood estimate means another. If these assumptions are true, then those 2 estimates are the same. Now, why do we call it least squares? It's because we're minimizing the sum of the squares of the errors, minimizing chi-square, which is what we did in the last 2 slides. But the least squares estimate isn't always the maximum likelihood estimate. It's only the maximum likelihood estimate under these assumptions. Just for reference, some properties of our ordinary least squares solutions. The first property is the most important one from our perspective. If our assumptions are correct, then our ordinary least squares solutions will produce parameters that are unbiased with minimum variance. In other words, there is not another estimate that you can come up with, another estimator, for the parameters of our model that produces unbiased estimate that has a smaller variance. This is the best you can do. In fact, we have an acronym for it. We call it BLUE. This is the best linear, unbiased estimate that we'll be able to come up with. But that's only true if our assumptions are correct. We have a few other mathematical facts that come out, which I won't go through. And then I'll just mention one useful thing to maybe as a double check. The best fit of your best fit line always go through the point x bar, y bar. So if I have a set of data, I can calculate the mean of the x values in my data, the mean of the y values in my data. And we know that our ordinary least squares best fit line will always go through that point. All right, let's look at what we've learned. As always, you should be able to quickly and easily answer these questions. If not, you should go back and review the lecture material again. First of all, what is a residual? What are the desired properties of a best fit parameter estimate? Explain what a maximum likelihood estimate is. And finally, what are the assumptions of ordinary least squares estimation? That's the first part of our three-part series on reviewing regression. In our next lecture, we'll go into a little bit more depth by looking at a matrix formulation for least squares regression. Till then, thank you.